So I am going to prove the equivalence of the various forms of the beta function because either you guys really like chalk on chalkboard ASMR or because some of the techniques used are pretty useful. But again, the beta function is something that has mathematical utility. It solves a couple of classes of difficult integrals. Lets us go back and solve some physics problems that we had needed to estimate or simplify before. And it's also useful in and of itself. It shows up directly in the physics of like adhesion and quantum mechanical scattering, a couple of other places in StatMech that I'm probably not too conversant with, as well as its pure mathematical utility. So this is what we've conjectured so far. So this is definition. So we're going to define the beta function through this polynomial-esque integral. So integral from 0 to 1, x to the p minus 1, 1 minus x to the q minus 1 is beta function beta pq. And it turns out, this is what we'll show, is that it's given by this form, which obviously relates it to the gamma function, because these factorials. And then along the way, to do this, we'll derive the trigonometric form. So again, the utility of this is a couple of the techniques used will be important and show up a lot. And secondly, we get another form that lets us integrate another class of integrals. So the proof of this, just write it down. So we'll start by just the definition of what m factorial, n factorial are in terms of gamma functions. So that would be m plus 1 factorial, n plus 1 factorial. And we know what those look like in terms of integrals. The only thing to be wary of is we got to use different dummy indices. So I'll use t and v, I guess I did, which is great. So integrate over t. And then we'll integrate the second one over a different dummy variable, call it v. So those are just those definitions applied directly. And then the plus 1 and the minus 1 go away. Now I'll just combine them. And you can probably guess where we're going with this. Is we have a 2D integral, so we have something that kind of looks like an area. So what is the area that we're integrating over? Well, it's the first quadrant. We did this when we integrated up e to the minus y squared, I think we did, so the famous normal integral. So we have positive some variable, positive some other variable. We'll call this the v-axis, we'll call this the t-axis. So essentially what we're doing is we're doing first quadrant. And what this is saying is this is like a D area, and it's a Cartesian or rectangular-like D area. Okay, why would we do this when we could do this in polar coordinates instead? What does that do for us? This turns two integrals into one. So the problem with doing that is when we pulled this trick before, what we were able to do was deal with this integrand. We had a y squared and an x squared in there. And we don't have a y squared and an x squared in there this time. We have just a t and a v. So we're actually going to do two things at once in our change of variables. We're going to lean towards doing polar coordinates, but before we do that, we've got to turn this into the type of integral that we already know how to solve, which has squareds upstairs. So long story long, we're going to change variables to start working towards polar coordinates in the following way. So the first thing we're going to do is define t is x squared and v is now equal to y squared, making dt to x dx and dv is to y dy. So that's our change of variable starting to go into polar coordinates. So we'll write that for one line and then be able to go into polar coordinates. we got a couple of 2's up front. I think I'm missing a 4 in my notes. And we have the thing in the exponential that we want from our normal type integral. Okay, so the point of that was that we have something that we recognize as being amenable to change of variables a second time into polar coordinates. And aren't we happy we didn't do this on Zoom? So we'll call it r squared. So now we get to change variables into polar coordinates. Okay, so the dx dy, that's just a piece of area, right? So that's dx dy. And the dx dy, because that's a piece of area, we can express that in rectangular, but now we want to express that in polar. So that would be r d theta dr, right? So the usual piece of area in polar coordinates. And then we have our change of variables. So this isn't a trig sub. This is just literally changing variables into polar coordinates, right? So x squared plus y squared equals radius. So x, therefore, is equal to r cosine theta. Y is equal to r sine theta. And then our limits of integration, the last thing that we have to express. What does the first quadrant look like in polar coordinates? Well, r goes from 0 to infinity, and theta goes in between 0 and pi over 2. Okay, so that's everything. We've changed the variables, we've changed the limits of integration, and we've changed the differentials, which is essentially dA. So after all that, we end up with something that's not nicer looking, to be honest. But does have a form of dealing with that integral that we're in a better position to handle. So we'll put the theta integral first, I guess. Okay, this is the magic trick that happened last time, is this r and this r squared allowed us to have a perfect total derivative inside of our integral. And it looks like that's happening again, except all of this stuff. So we didn't bargain for this. 2n, that's an n, sine is n. Okay, so this is the difference in between just the normal integral, the error function, that we did in class, and this is that these pieces exist, and we have a non-trivial theta integral. Yuck. So these have two parts. They're separable, so we can pull them apart. And we have this bit and this bit. So we'll call them star and double star, I guess. So we'll put the 4 there. So we have the r part, and the r part looks like this. Okay, we had that, but then it came at this terrible penalty. So we have r, but then we have 2n plus 1 more r's, and then we have 2m plus 1 more r's. So all in all, we have r to the 2n plus 2m plus 3 power dr. Completely off the rails. This is so terrible. And then pi over 2, all of the trigonometric bits. So that's sine theta 2n plus 1. Okay, so this is what we got. We really just wanted that. Oh no. But don't worry, we have a way of solving this. So we'll call this, label these two terms, call this double star. And we'll label this term star. Actually, not include the 4. Put that in later. Okay, stop, think for a minute. How on earth, because you have seen things like this. What does this look like to you? Have you seen something that looks like this? Integral over r, e to the r, and then some grody stuff there. and then this. So we have 2 bits. We'll work a little bit and do a third change of variables. But it's honestly just aesthetic. Because if you could stare at this for a minute, convince yourself that living inside of this is one single gamma function. Right? So we're just going to change variables on single star to show for a fact that that really is a gamma function. But you don't really need to do that if you're good at decrypting the various terms. So the claim is that star is a gamma function. Thing is gamma of what? Because that actually looks like a bit of a mess. So we'll change variables again. And we'll change variables to Q. I don't know. Let's do Q. So Q is R squared, therefore dQ is 2R dR. And then R to the 2m plus 2n plus 3 would be equal to R times R 2m plus n plus 1. That's kind of what we want. And then plugging, showing you why I'm doing this, I guess, first, is we have e to the minus r. Sorry, this is squared. I wonder why that looked really weird. So that's why we want to do a change of variables first. So now we have e to the minus r squared. R2m plus 2n plus 1. So this is just rewriting r, dr, plus 3, is equal to 1/2 from the dq part. E to the minus t, now we look like a gamma function. T to the m plus n plus 2 minus 1. There's a reason to write it that way, dt. Stare at this, tell me it's a gamma function. You're right, it's a gamma function. So this is equal to 1/2 gamma of m plus 1, n plus 1, m plus n plus 2 is m plus 1, n plus 1, minus 1. So this is equal to gamma of m plus n plus 2. Or, if you want to remind yourself what the gamma function meant for us at the outset of this whole gamma function journey, it's equal to that. Okay. So this, with a little bit of change of variables or just some squinting, basically replace the r squared with a t. This first term is just a gamma function. Okay. So now we have to work on the second term. So this double star part, and this is why we do this proof, is this actually turns out to be a third form of the beta function. So our final claim, let's be pretentious and let's call it a lemma. How about that? We haven't used any of those yet. Claim is that this thing is equal to that. So this is the equivalence in between those two integral forms. The one that I erased and was our original definition of the beta function, and this, the trigonometric form of the beta function. Okay, stare at that for a second, maybe convince yourself that it's possible. Actually, this is totally doable. really quickly, what would you use as a change of variables to show that this is correct? I think it's pretty straightforward. Might take like a couple of tries. Don't worry too much about the 1/2. It'll happen naturally for you. So looking at the limits and looking at the powers, it's really the theta that'll get you. But pretty clearly, we're going to want an x to be equal to some trig power squared. And it turns out this does it for you. So if you do this, you get dx equals to sine theta cosine theta d theta. And then 1 minus x is equal to, therefore, cosine squared theta. 1 minus sine squared theta is equal to cosine squared theta. And then this has the right limits because when x is equal to 0, we're at the limit 0. Right? That's why we choose x for sine. It's got the right limits. And when x is equal to 1, then sine is equal to pi over 2. Right. So that has the right limits. Okay. And then we get the plus ones are taken care of naturally. So these plus ones come from the change of variables in between dx and d theta. So that turns out to be our change of variables. And if somebody is squinting at me as I say that, you're right to be squinting. Because we actually proved something else along the way. So using this change of variables, get integral from 0 to pi over 2. So sine squared, that's what we put in for x. And you can take issue with that, and I applaud you for doing so. Cosine squared theta n. And then our change of variables, that's the 2 and the 1/2. Cosine theta, sine theta, d theta. Right, so just unpacking this. And then our change of variables, clearly this is x, and this is 1 minus x, and that's dx, and that's 1/2. So 2m plus 1 and then cosine 2n plus 1 theta. And we started by just writing this, so I left off my 1/2, so I should have a 1/2 here. So there. So this is the right change of variables. Everywhere on the right-hand side we see x, we put in sine squared theta. Somebody may have realized that you could actually do cosine squared x here too, and everything else works. You would get the same dx, right? The derivative of cosine squared x, get the same thing. You would get the same limits are 0 and 1, just flipped. Get a minus sign there, get a minus sign there. It's kind of a subtle observation, but it's true. And it turns out that if you follow that line of reasoning, you've actually just along the way showed that the beta function is symmetric on its indices. So beta qp equals beta pq. So we could have actually completely flipped you can see it right here in the change of variables, right? So you can also see it from the description in terms of the gamma function or the factorials. Okay, so what we have is this. which has a practical utility. One or the other of these might be easier or might be directly what you can read off of, like a free body diagram or an equation of motion, is that we have a relationship in between polynomial and trigonometric integrals. Cosine theta. And now I'm just going to be kind of goofy with it, and you can flip the m and the n. So it's totally not obvious here, the fact that you can flip the m and the n and it's the same, but with the cosines and the sines, it seems a little bit more straightforward. And in some sense, right there in the change of variables, we proved that this is true. Okay. So do you want to do polynomial integrals? Do you want to do trig integrals? Both of these are fine. Usually what happens is people don't want to do those, and they do want to do those. So you can turn the trig into polynomial. So that is the proof. What we'll do is we'll come up with some examples of how you would show up, how you would find these in nature, and how you would not even relate them to these, just relate them to gamma functions. Is actually the easiest way to do this in practice.